Hello everyone, I am Abdul Alam Khalib and I am so excited to be here with all of you guys today. I hope you are all having a great day. As the famous scientist Paul Dirac once said, pick a flower on earth and you move the farthest star. What he meant is that even the smallest thing you do here on our planet can have big effects that reach all the way to the stars in the sky. It shows us how everything on Earth and in the universe is connected, like a delicate balance. This might be our first time learning about quantum computing, but remember, taking this small step is something to be really proud of. So, today we will learn the Bell state algorithm, quantum teleportation, and we are going to learn how to operate a real life quantum computer using Cascade and Bernstein-Veserani algorithm. So with that, let's start. So first, what is the Bell state algorithm? Bell state algorithm are special family of quantum state that exhibit remarkable properties. They are like twins of quantum state, and when we measure one, we instantly know something about the other, no matter how far apart they are. Bell state play a crucial role in various quantum applications, from quantum teleportation to quantum cryptography. So, how why Bell state algorithm? It's actually creates a entanglement state. What is a entanglement state? Let's learn that first. So imagine I give you two box, and one of them have wait. Let me draw. Okay, two box. One of them will have red value, and another box will have blue value, but we don't know in which box we'll get that those results. So imagine I give you one of the box, and I take this box along two, and when you open the first box, you will learn that one of them will have let's say, imagine you have the red value. So when you learn that the box I gave you had the value red, then you will instantly learn that the box I have, the second box, will have the blue value. So this is basically the entanglement. That means if you learned about one state, then you will instantly learn about the second state. So let's learn how to create a Bell state. First, we have to start with two qubits with zero state. We have to apply HK to the first qubit, and control gate, C naught gate, to second qubit, where the control target will be at the second qubit, and the control will be at the first qubit. So there are four types of Bell state. For input 00, we will have a superposition of 0 0 0 and 1 1. For Bell state 2, or for it will take the input 0 1, and it will give us a superposition of 0 0 and minus 1 1. And the third Bell state, it will take the input value 1 0, and they will return the superposition of 0 1 and 1 0. And the fourth Bell state, it will take the input state 1 1, and the output will be a superposition of 1 0 and minus 1 and 0. So how do we code this algorithm? First, we will export all the import all the necessary libraries here. Then we will create a quantum circuit using 2 qubit and 2 classical bits. Then we will apply the H gate or Hadamard gate to the first qubit and apply a C naught gate to the first and second qubit, like this. So why this particular circuit creates an entanglement state? Let's try to visualize it. Control P. So here from the previous class we have learned that when we apply 0 to the H gate, it will return a superposition of 1 and 0, 1 and 0. So and in second qubit the con at the second qubit we have the initial state 0. So for the all the one for the value 1, this x gate will act as a x gate and it will change the value to 0 to 1. And for the value 0, it won't change the superposition state, and it won't change anything, and it will just return the value 0. So what we get for everyone, we get basically for one we get 0 and 1, and for 0 we get only 0 and 0. There's no another thing. So because of this we say we get two value. One is 0 0, or another is 1 1. So when we measure that, when we get the value 1 here, so we can instantly learn that the second qubit will be 1. And when we measure the first qubit to be 0, then we can instantly learn that the second qubit is 0, 0. That's why this is it creates what's it called, entanglement state, and provides a Bell state. So for second Bell state, the input was um, where it go? Input was 0 1. That's why we will apply for in this case the second uh, 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 hmm? So for the second case, we have to just apply a x gate to the first qubit, and this scenario is exactly the same as the first Bell state. And the for third Bell state, the input have to be 1 0. So what we will do, we will apply x gate to the second qubit, so that the input state will be 1 0, and then we apply the same thing here, as it was same at the as the first Bell state, and it will return the value 0 1 or 1 0. In this case, when we measure that, if the first qubit was 0, then we will get the we will instantly learn that the second qubit will be 1. And when we measure the first qubit to be 1 state, then we will instantly learn that the second qubit will be 0. So this is the Bell state, second Bell state. So for that was this third Bell state. And for Bell state, for fourth state, we need basically the input state to be 1 1. So that's why we will apply x gate to both qubit, and then we do the same apply the same circuit as we applied to the Bell state 1. and when we measure it, we get a phase 0 and phase pi of 0 1 and 1 0. So it's basically same, and but there will be a negative in front of a superposition state 1 0. So that's a change. So basically if we look clearly, the then we can see Bell state 1 and 2 basically the same, but there is a negative value in front of 1 1. And when we observe Bell state 3 and 4, this superposition state looks same, but there is a negative value in front of 1 and 0 at the Bell state 4. So this is Bell state. So why do we need a Bell state? Bell state might sound like complex, but it's not. It's just basically a ACE gate and control not gate. It is necessary for quantum communication, quantum cryptography, and quantum computers. So next we will learn teleportation. This will take uh, time. So what is quantum teleportation? Imagine being able to send a quantum state to your friend instantly. That's what quantum teleportation allows us to do. It's like teleporting your favorite sci-fi movies, but with quantum information. Here's a case. It can't just copy and paste quantum state like regular information. Instead, we use a combination of 3 qubit and some quantum tricky to send quantum information securely. So quantum teleportation, in quantum teleportation we don't clone the information, we just port the information, the original state of state of the information to one place to another. So it follows the no cloning theorem. So that's why it's important to remember that to teleport something, to teleport a quantum information, we need to obey the no cloning theorem. So this teleportation algorithm does not clone any state. Instead, it teleports. That's why it follows the no cloning theorem. So let's create a teleportation circuit. First we import all the necessary what is called all the necessary functions like we did before. Then we create quantum register with 3 qubit. We have to remember that to teleport a message we need 3 qubit, one for the message and two for entanglement. And we need 3 classical bit. Then we create a circuit with that. So first we have to apply X gate to the no first we have to create the information we want to send. For this case I want to send a message that have a quantum state 1. So that's why I applied X gate to the first qubit. Then we will create an entangled qubit between the first qubit and the second qubit. For that we learn that we apply Bell state algorithm. So which basically entangles a qubit between the qubit 1 and 2. So for that we apply Hk to the second qubit and Xk to the first and second qubit. Then we have to entangle the qubit 1 and the with the message state qubit 0. For that we apply cx gate to the to here, I mean qubit 0 and qubit 1. Then we apply h gate to the qubit 1. What it creates, that it entangles between qubit 1 and qubit 0. Now we have to measure the qubit 0 and qubit 1 and save it to the classical bit 0 and 1. Now here we have to put if else factors. When we measure the value 1 from the classical bit, we apply control x gate to the third qubit, and the control bit to this first qubit. And if it measures 1 from the classical qubit, then we apply control z qubit to the third qubit, and the control qubit to the first qubit or message qubit. Then when we run it and measure the qubit 1, we will get the value of this first message qubit. So when if we added a ace gate here, then result of the fourth qubit will be a positive state, or the superposition of 0 and 1. If we applied x qubit and x gate and h gate here, then we will when and then measure the third qubit, we will get the result of superposition of 0 or -1. So so what it basically do, whatever result the first qubit have, it will send the message to the third qubit. And when we get the result, it will the show the result to the third qubit. Let's try to visualize it in quantum experience. I mean quantum experience. Oh, my laptop. So this is the same circuit we coded there. See, when there is look at this result. When there is a x gate here, we get a value 1 here. When we remove the x gate from here, we will get a 0 state here. Let's see. Yes, we get the 0 state here. So if we apply h gate here to the message qubit, we will get a superposition of 0 and 1. See, the 50-50 probability of 1 and 0. Probability of 1 is 50%. If we apply x gate to here, then we will get a superposition of 0 and -1. See, it turned red, and it gave a phase pi, which basically means negative. See, it gave the value minus. So if we apply something random, let's say t, it will give the value. So basically whatever we are putting here, it will the result will be shown at the third qubit. It is basically transporting the state of first qubit to the third qubit. So this is the teleportation. The first line of the code here, It's basically mean we are putting a control x qubit, and we are doing a 180-degree rotation to qubit, the second qubit and third qubit. And if we measure 1 here, it will work as a control x, otherwise it won't act as a control x. If and for this is the same. If it get the value 1 here, it will act as control z gate. Otherwise it won't act as control z gate. Uh, and this is basically this. So after measuring there, we can see it is giving us the value 100, because we applied a x gate at the first qubit here. That's why we are getting 1, then 0, then 0. That's why it's giving us the value 100 here, and the phase is 0. So how do we get a result from the original qubit? So this is important. First we import IBM Q from Cascade. From IBM Q we are going to get all the necessary backends, and to get all the backends, we are going to need a API token, which is private. Don't share this information with others. So to do that, we are going to type IBM quantum experience, hit enter. Then we will go IBM quantum platform. So it will ask you to log in. It didn't ask me to log in because I already logged in. So this is where we will get the IPI token. Then if we click here, then it will copy the IPI token from here. Then copy it, and then we have to paste it here. I'm not pasting it here because it's totally private. Don't share this information. Don't share your API token with anyone. So if you think that your API token got public and you want new, then you have to click here to get new API token. So to save your account, we have to program a code IBMQ dot save account. Then we will paste our API token here, and then we apply override equal to true. If Then we will I didn't run this code because it will take time. Then we have to get all the provider. How do we get all the provider? From IBM Q dot get provider, we have to select a hub. For now I am using IBM Q. Then there are lots of backends there. Some are really busy, some are least busy. So that's why we to get all the least busy quantum backends, we have to apply this function list busy. Then provider dot backends. Then we are adding filters equal to lambda x, and x dot configuration dot n qubit larger than 3. Why did we apply 3 here? Because we need a quantum compute. We need a backend that is at least that has at least 3 qubit, because here we created a circuit with 3 qubit. That's why we need at least a backend that have at least 3 qubit here. Then and not x dot configuration dot simulator, because we don't want simulator, we want a real quantum computer. And x dot status dot operational is true. Now if we run this code, it will print out the backend name list busy backend. I'm not running because it's completely private. Then we do the same we as we did previous class. We will execute yeah, the circuit with the backend we just get from here. I added the time to measure the time, but it will depend on the it will depend on the provider. If you are lucky enough to get access early, then you can run this as quickly as possible, but for me it took a month. But don't worry, I don't know. So this code basically returns the time and count it took, and then we plot the histogram from here. So uh, with this code, we can from the beginning, so we first create a circuit, then we applied it to a real life quantum computer. So and you have to copy your API token from here. So this is the quantum teleportation. Why do we need quantum teleportation? We need it for secure communication, for we need for quantum internet, and we need it for quantum cryptography, and there are lots of algorithm. It's just basically I just introduced you to these three concepts, but there are other field that uses quantum teleportation. So now we are going to learn Bernstein-Vaserani algorithm. It will take time because Bernstein-Vaserani algorithm is basically um, oracle based. So it basically means we are solving oracle based problem. What's oracle based problem? So imagine I gave you a box with seven string, uh, uh, where you can either put 0 or 1, but I gave you only one attempt to open it. You need at least seven terms to open that box, because it's basically called brutal force. So imagine you have a oracle box that takes n qubit and produces a single qubit as output. This oracle box has a hidden n qubit secret string that determines the output. Your task is to get the hidden string from at least number of queries that get the result. So the classically to unveil the secret string, you need to make n queries uh, to open that box, one for each bit of the secret string. This is known as the brute force approach, and it takes n queries, which is linear to the problem size. Now let's introduce to quantum magic. The Bernstein-Vaserani algorithm is a quantum algorithm that can unveil the secret string in a single query, regardless of the problem size n. Yeah, that's why I made a 2-minute video on this and posted in the the I have posted that earlier. If you have watched it, no problem. I will explain it again. So in image, so let's see. We observe we have a oracle box here. Let me make a separate. Yes. So we don't know what is inside in this oracle box. So oracle box is basically made of CX gates. Hmm. So we don't know what inside this box, but we want to decode this code. Imagine we cannot see this code, the box. So to get get the value, let's say here we have a seven seven string long a hidden code. So to get the result we need at least for seven string we need 8 qubit, one extra to get the result. So in previous class we learned that because of this x gate and h gate, the target qubit controls the control qubit. That's why when we for this, let's clean this. Control Z, Control Z. Okay. So here we have the value 1, and here we have the value 0, 0, 5, 0. So let's say here for this target qubit, it flips the result here, and we get this the result 1 here, 1. Then this will also change, sorry, will also change the result to 0 to 1. Where is it? And this will also change to 0 to 1. And as there is no control qubit here, and in here, that's why we won't get any result from here. So this will be 0. Control C. This will be 0. It will be 0. So from here we can see that we get the value 0, 0, 1, 1, 1, 0, 1. So that's how we get the secret code from here in single query. After measuring it we will get the answer 00111101. So how do we code that? So basically we will import all the necessary codes from here, and we will save the hidden code generate hidden binary string from here. First we need to check the length of the string, because if the length of the string is n, then we need n plus 1 qubit. So from here we get the string is 7, then we need 8 qubit. So for this we will create a quantum circuit that have length plus 1 qubit, and length plus 1 classical bit. So QC equal to quantum circuit, where length qubit the qubit is n plus 1 and the classical bit is n plus 1. Then we will apply x gate to the at the end of the qubit. So x gate and the position of it is the length. Then we add barrier here. Then we will apply h gate to all the qubit here. Here we auntie to class নিচ্ছি। um, so hello. Okay. Here we can see we for we want to add a qubit to all the qubit here. How do we do that? We apply for loop here. For the range n plus 1, we will save it to the I, and we apply h gate to all the qubit here. Then we will add this oracle box. So basically this part of the code won't be available, so we have to import it from somewhere. Then we apply edge gate again, but for this case we have to apply the edge gate to only n qubit, not n plus 1 qubit. So after adding the edge gate, then we will measure all the qubit and save it to the classical bit. After running the code, we will after running the code, we save it to the output state variable, and then when we print this out, we get the hidden binary code 01101. So from the so the hidden binary string is 011 and from output from the quantum circuit is basically the same. So that's how we are getting the result. So because of this, each time we run this the code, it will give a different kind of circuit. Yeah, see, this circuit is not similar like before, and it will give a different answer. So for this code 0 0 0 0 0 1 0 hidden binary string, we are getting the output from the quantum circuit, we get the same result. So this is the Bernstein-Verzner algorithm. I uh, took take this uh, class really fast because I am really sick. If you have any question, please ask. Please. Mm, anyone? If you have any question about, okay, yes, please. Everything. Any question about Bernstein-Verzner algorithm? Because I took that class really short, but I made a separate pre-made video on Bernstein-Verzner algorithm, and I have posted it on the Discord. So if you have any question about Bell state algorithm or teleportation, or If you are if you want to run the real life quantum computing quantum computer, if you face any problem, please let me know. So I am taking this class short. So yes, please let me know if you have any question, or I will end this class from here. And also about the quiz, please take that quiz before 20th October, and I will post today's quiz after this class. The sonar is better. If you have no question, any question,